Okay, so for the next two lessons, 4.5a and 4.5b, we've basically broken one lesson up into two because it's definitely too much content for a single lesson. Both lessons refer to different strategies for graphing quadratic relations. And now, obviously, that's what we've been doing for the last few days, but we've been dissecting all the different components of the vertex form and trying to figure it out from there. So we're going to take that knowledge and we're going to apply it to two strategies to hopefully make life a little bit simpler for you, or not. Well, I guess we'll find out. Okay. So the parabola of any quadratic relation we know is y is equal to a times x minus h all squared plus k. And we can graph this by applying all the transformations. Transformations of what? A, H, and K. Now remember what each of these represented. A represented how much we vertically stretch or compress. It also represented whether we should reflect in the x-axis. H represented how much we translated the entire curve, the entire relation, left or right, horizontally. And K represented how much we translated the entire curve vertically. Now, if you want to try and keep these two apart, H and K, H is for horizontal. H means left and right. Okay, so we're applying the transformations. Now, the key here is that they're all done in the proper order because multiplying can change values really quickly if we don't do things in the correct order. So the first strategy we're going to learn is something called the mapping strategy. So this method of graphing a parabola is done by mapping notation. All that really means is that we're going to map the x and y components of the original parent relation, y is equal to x squared, and we're going to map it to the modified versions of those same values in the new relation. You're like, I don't fully understand. Well, we'll come back to that in just 1 second. So if we use our normal x values for our y is equal to x squared relation, our parent relation, we get -2, -1, 0, 1, and 2. And whenever we did this, we always got the same numbers, 4, 1, 0, 1, and 4. Great. So this is the parent relation. And what we're going to do is we're going to map each of those values to their corresponding values in the new transformed relation. Okay. And I'm going to take a step back to the previous lesson in a second just to show you how it still applies to the previous lesson in the same way that it does here. So here are our steps. First, we're going to create a table of values with 5 key points. Okay. For the quadratic relation y is equal to x squared. Done. We just did that over here. Okay. Create a second table and transform the x and y values as follows. What we're going to say is we're going to add h to x, and then we're going to make the second column, instead of just y, it's going to be a times y plus k. And you're like, what? Where does this come from? Well, x plus h. Remember where our vertex is. Our vertex is always at h, k. So if I take the original x value and I add on h to it, I'm adding on the horizontal shift, the horizontal transformation. Remember, that's what h represents, is how much we're transforming it horizontally. So we're just saying, well, let's map it to its new location by simply adding h to it. Similarly speaking, over here we have a y plus k. Well, what does a represent? A represents how much we vertically transform, vertically stretch or compress each y value in our original curve. So let's say, for example, a is a 2. That'd be 2 times 4, and that would give us 8. That'd be a vertical stretch. Now, that's why we multiply it, because it's scaling the value, each individual component. If that's a negative, then it would also reflect the value. It'd give us -8. Okay? And then at the end, we add on the k. This does the exact same thing as adding on the h to the x component. We're vertically transforming whatever value we just calculated. This is where the order, as we talked about over here, the proper order matters. So if we accidentally did something like this and put brackets around there, that would completely change what our end results were, and that's not what we actually want. So let me just erase those components here. Pop, 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 pop. There we go. All right. I don't know how I managed to erase just the brackets, but I did. Sorry, everything's lagging here. So it's catching up. Our value here, ay plus k. There we go. AY plus K. That's where those values actually come from. They actually mean something. They're not just something somebody made up. Just saying, how much do we shift horizontally? So let's take every X component, and we're going to shift it by H. And we're going to take every Y component, we're going to multiply it by A, and then we're going to add on K after that. Okay. So to create a second table with this transformation. Then what we're going to do is we're just going to graph. And we're going to connect the points. And that's it. Now, when we're describing the transformations down here, we always want to go in a very specific order. So whenever we're describing our transformations down this final little piece, we always want to do it in a very specific order. So A tells us the first thing, which is, do we reflect in the x-axis? So let's talk about reflections. That's the first thing we're going to state. Then we're going to talk about vertical stretches and compresses. Stretches and compressions. Stretch and compressions. Stretches and compressions. So the first thing we're talking about is A. Okay. The second thing we're going to talk about is H. Really, H and K are simultaneously, but typically we look at H first. So we're going to talk about horizontal and vertical translations. So how much is it shifted left and right and up and down? Remember, H is for horizontal and K is for vertical. Alrighty. Now, this is all the information we need to know. So let's go and apply this information. So here we have a much more complicated equation than we're used to. I'm saying that we can solve all of the problems that we were doing before just by applying our mapping notation. Now, let's start off with our parent relation. So we have -2 all the way to +2, same x values that we always do. So we're going to end up with 4, 1, 0, 1, 4. Now, our first column is going to be x plus h. Well, what is h? Well, let's look at our graph, or let's look at our expression. H is right here. It's our middle term. So we take the value of the 2. So it's 2. And we take the opposite sign. So it's going to be a +2. Okay. What is our k? Our k is -3. Okay. And what is our a? Our a is a 2. So we have all of our information now. What does this tell us? H tells us that we have a shift to the right by a value of 2. K tells us we have a shift down by a value of by a value of 3, not a value of -3, a value of 3. Remember, it's the absolute value. So it's -3, and this is a shift down by a value of 3, by 3 units. Why is that not showing up? There we go. So we have x plus h in the first column, and the second column is a, y plus k. So x plus h. So for every value of x in the parent relation, we're just going to add 2. So -2 plus 2, that's 0. -1 plus 2, that's 1. 0 plus 2 is 2. 1 plus 2 is 3. And 2 plus 2 is 4. So there's our x components. Now for our y components, we're going to take the original value, which is a 4, and we're going to multiply it by a. Okay. So I'll write it out, the first one, so we can see what's happening here, so you can see this. So our original value, which is a 4, and we're going to multiply that by a, which is a 2. This handwriting, there we go. And then we're going to add on to that k, which is a -3. So we're going to add on -3. So 2 times 4, that's 8 minus 3, which gives us 5. And that's where that comes from. Now we just rinse and repeat. We take the original term, which is a 1. We're going to multiply it by a, which is a 2. So now we're at 2. And then we're going to add on k, which is a -3. So 2 minus 3 is -1. We just continue this process. So 2 times a, which is 4. Okay. And we're going to subtract 3, which is just going to give us, sorry, I made a mistake there. So we have y, which is a value of 0. I was looking at the wrong value. So 0 times a, that's still 0. And then we're going to add on our k, which is -3. Now we're going to take our next one. 1 times a is 2 minus 3, which is going to give us -1. And 4 times 2 is 8, minus 3 gives us 5. And just like before, our middle represents our flip. There's our vertex again, 2, negative 3. Well, we knew that just by looking at our equation, hk. So we didn't really have to think about it, but we will. So our job is to graph the relation. We don't need to graph the parent this time. We're just going to go right to it and graph the new one. So in this case, we have 0, 5 right up here. We have 1, negative 1 all the way down here. And then we have 2, negative 3. And then we have 3, negative 1. And 4, 5. Right up here. Now we got to try and connect these dots without it looking terrible. I'll give us a solid 6 out of 10 on that one. So we have an x, we have our y, and we write our entire equation here as y is equal to 2 times x minus 2 squared minus 3. So that was a fairly complex equation, but it didn't take us that long, and we spent the entire time explaining everything. So now let's go down and fill out our chart so we can see exactly what we did here. Let me just kind of pop that down a little bit. So what was our coordinates of our original parent relation? Yes, the vertex was still 0, 0. And yes, it opened up. And its equation of its axis of symmetry is just x is equal to 0. And over on our new relation, our transformed relation, where is our vertex? Our vertex is at hk, which is, and we can see it in the curve too, which is at 2, negative 3. Remember, this is just hk. Don't overthink it. It is still opening up. Where is the new vertex? X is equal to h. So that implies that x is equal to x is equal to 2, which we can see. We could even draw it in here if we needed to. All the way down there, and x is equal to negative 2 for our axis of symmetry. Great. So now we have to describe all of the different pieces, all the different things that happened, okay? Now, what I want from you is keep it as simple as possible. That means I want a bullet point for every transformation that occurred. So we start with the first one. We start with reflections. Was there a reflection? There was not, so we don't have to say anything. Was there a stretch? Absolutely, there was a stretch. There was a vertical stretch by a factor of 2. We can see right by the A component here. So a vertical stretch by a factor, BAFO, of 2. All right, now we go into HK, horizontal and vertical translations. So let's start with the horizontal. Was there a horizontal transformation? Yeah, there was. There was a horizontal transformation to the right by 2. We already wrote that over there. Okay, so horizontal transformation 2 units right. What about vertical? Yeah, certainly was. We have a vertical translation down 3 units. Oops, my graph is getting wonky on me here. Just give me a second. All right, let's try this again. A vertical transformation in this case, 3 units down. And that's the whole thing. Now, if you go back to yesterday's lesson, which is up in here, if it ever updates the graph, and you apply what we just did to our table of values here, you're going to find that we actually did the exact same thing. This is really our x plus h. Our h is negative 2. If negative 2 plus negative 2, oh, there's that negative 4. Over here we have our ay plus k. And the math will actually still work out. We did the same thing yesterday. We just did it without realizing it. So let's go down. Let's go down to another example if we can here. We're going to do 2 more examples, and then we'll finish that for the day. So this one is a little bit more clunky because we have some fractions in here, but we still have to do all the work. So let's look at our AHK. What is our A? Our A is the value in front of the brackets. That's a negative 1/2. Everybody's sure excited to see that. We know we are. So that means we have a reflection in the x-axis, and we have a vertical compression by a factor of 1/2 because it's less than 1. All right. And now what about our H? Our H is the value inside the brackets, which is a 1, and then the opposite sign, so negative 1. All right. And our K is just the value on the outside, which is a 5. That means that our vertex is located at negative 1, 5. We know that for a fact. So there's all the information we needed to do. Now let's fill out our chart. So on the left-hand side, we have our parent equation. Our parent equation is, we're still using the same values of x, so that means that our y values are always going to be 4, 1, 0, 1, and 4. Okay. Oh my goodness. There we go. Now, on the right-hand side, we remember this is x plus h. X plus h. I'm just going to write this in here. X plus h. But in order to make our life a little simple, let's actually write the math. That's x plus negative 1. So that's x minus 1. Okay. Now over here we have a y plus k. Well, what is a? A is negative 1/2. Okay. Multiplied by whatever y we have, and we're going to add on k, which is 5. So now we have an equation for each side. Let's just fill it out. X, negative 2. Negative 2 minus 1, negative 3. Negative 1 minus 1, negative 2. Sorry. Negative 2. This 3 is not showing up super great. There we go. Negative 2. 0 minus 1, negative 1. 1 minus 1 is 0, and 2 minus 1 is 1. Makes it a lot easier when you just write it out there. Over here on the next one, we have a negative 1/2 times our y. So 4 times 1/2 is 2, but we got a negative, so we have negative 2. Plus 5, that gives us 3. All right. 1 times a negative 1/2, that's just a negative 1/2. Negative 0.5. Plus 5, that gives us 4.5. Now you could write it as 4 1/2 if you want, but we got to graph it, so the 0.5 is probably going to be easier to graph. So the next one, negative 1 times negative 1/2, that gives us 0.5. Plus 5, did I do that right? Negative 1 times, oh, it said that is 1/2 plus 5. I think I'm off by a little bit. Where are we seeing this here? So we should have negative 1, and that should be 5. Yes, that's right. And then 0 times that is just going to be 5. What is going on? My math is off here. Oh, I see. I was applying it to the wrong values here. I apologize. So 0 times negative 1/2 is 0. 0 plus 5 is 5. Silly me. I was applying it to these values for some reason. I don't know why. And then our next one is a times y. So that's a 1. 1 times a negative 1/2 is just negative 1/2. Plus 5 is going to give us 4.5 again. And then our last one, our y value is 4 times a negative 1/2 is negative 4. Negative 2 plus 5 gives us 3. If some of you are trying to figure out where these numbers come from, let me show you the equation just so you can see it. So we have negative 1/2 times our y value here. So we're just showing this one, which is the same as the one up here. Okay. Negative 1/2 times the y value, which is 4, and we're going to add on 5. So that's the same thing as saying negative 4 over 2, which we know is just negative 2, plus 5. That just gives us 3. That's where the number's coming from. Okay. So let's graph it out over here. Now again, we have negative 3 and 3. So negative 3 all the way up here, just a 3. And then we have negative 2, 4.5. Now it's hard to be perfect on this, so just do the best you can. If we had a better resolution of a scale, it might be a little bit easier. And then we have negative 1, 5. right here. And then 0, 4.5. We've looped back around. And 1, 3. Right here. So now we're going to draw our curve in. That was atrocious, but it'll do. And we label y is equal to negative 1/2 times x plus 1 all squared plus 5. That's the entire curve. And if we want to put the axis of symmetry in here, we can draw it right down the middle here because that's where it's going to be. Alrighty, so we fill out our table the same as we always do. We know our parent equation. Its vertex is at 0, 0. It opens up. And its equation of axis of symmetry is x equal to h, which is x equal to 0. Over here in this much more complicated relation, where's our vertex? Well, we can look at it and we can see that it's at negative 1, 5, but we could also just look at our hk. So this is at negative 1, 5. And then our direction of opening, oh, it's going down this time. How do I know? Because a is less than 0. So it's going to open down. All right. And the equation for our axis of symmetry is always x is equal to h. So x is equal to negative 1. Now, what are all the things that happen this time? Well, we start off with our a. Was there a reflection in the x-axis? Yes, there was. So reflection in the x-axis. And was there a vertical stretch and compression? Yep, there certainly was. And a vertical compression, because it's getting smaller, because it's a value of 1/2. By a factor of 1/2. Okay. Now what about our h and our k? So this is all about horizontal and vertical translation. So did it shift horizontally? Well, looking at our h value, yep, it shifted left by a value of 1. And our verticality, it's shifted up by a value of 5. All right. So let's put this in here. So a horizontal translation, 1 unit left. One unit left. And our vertical translation, yes, vertical translation, in this case, 5 units up. That's all the change that occurred. So if I were getting you to describe this, you'd get 1 mark for every single point here, maybe a 1/2 mark depending on the breakdown of the question, but you'd only get credit for specifying all those values, all those changes, as well as the values that they're changing by. So for example, by a factor of 1/2, 1 unit left, 5 units up, that kind of thing. So we have one more question just to demonstrate, and in this case, this one is forcing us to make sure that we understand where all the values are coming from. Okay, so on the left-hand side, we still have our parent equation, still have the same x components, so we still have 4, 1, 0, 1, and 4. On the right-hand side, we're having x plus h, but what are these values? So let's take a look. First of all, what is the value of a? Now that's the stuff outside of the square, so that's negative 3. That tells us that we're going to get a reflection in the x-axis and a vertical stretch of 3 by a factor of 3. I could even write that down here right now because I know that for a fact. What about h? Well, there is no h. Inside the a times x minus h squared, in this case, we're subtracting 0. So h has a value of 0. That means that there is no horizontal transformation. Okay. And k has a value of 4. So what this tells us is that our vertex is located at 0, 4. It's good to know. All right. So let's fill this out. So this is x plus h. X plus h, that's just x. So nothing's going to change here. And over here on the right, we have a, which is negative 3, times y, plus k, which is 4. So we're going to take each x value, x plus h, which is just x this time, because h is a value of 0, and we're just going to get the same numbers. So negative 2, negative 1, 0, 1, and 2. Now we got to take each of the y values and apply it to the formula over here on the right, the equation on the right. So negative 3 times 4, that's negative 12. Negative 12 plus 4 gives us negative 8. We go to the next one. Negative 3 times 1, that's negative 3. Plus 4 gives us a 1. Negative 3 times 0 is 0, plus 4 is just 4. Negative 3 times 1 is negative 3. And we add on 4 onto that, and we're going to end up with a 1. And then negative 3 times 4 is negative 12, plus 4 gives us negative 8 again. Okay, this makes sense. Our vertex is 0, 4. We can see that this is where things start to reflect, the symmetry starts to apply. So let's put in and graph what we see. Negative 2, negative 8. Boom, all the way down here. Okay, and then negative 1, 1. Oh, up here. 0, 4. And then 1, 1. And 2, negative 8. That's a very tall one. Don't forget your arrows, our x, our y. We can label it. Y is equal to negative 3x squared plus 4. So we have our label. Let's fill out all our information. Vertex of the parent, still 0, 0. Nothing changed. And it's still opening up, and it still has an x equal to 0 axis symmetry. Our axis of symmetry here is actually still on the y-axis when we look at our curve. So on this one, where's our vertex? Our vertex is at 0, 4. We can see it right here. 0, 4. And is it opening up or down? Well, A is negative, so it's opening down. And we draw our axis of symmetry. It's still at x is equal to h, so it's still at x is equal to 0. And then finally, we have to label all of our details. So let's look at our A value. Has it been reflected? Yep, reflection in the x-axis. Was there a vertical stretch or compression? Yeah, there was. In this case, it was a vertical stretch by a factor of 3. That's the worst baffo ever. There we go. By a factor of 3. Now let's look at the h. Was there any horizontal transformation? Or there was not. 0. H is a value of 0, so we can just skip that. We go right to k. Vertical. Yep, there was. So there was nothing here. In this case, there was a vertical transformation up by 4 units. So vertical transformation. Oops. 4 units up. And that's it. So this is the mapping notation that we were talking about. And in the next lesson, we're going to get into another strategy, which maybe that one will help you get to the graphing piece a little bit easier. Everybody's a little bit different. But we need to know both strategies going forward. That's it for now.